Modern power grids are engineered around a baseline assumption of symmetry. Generators, transmission lines, and transformers are designed to operate as perfectly balanced three-phase electrical systems, with energy flowing in a smooth, predictable rotation. That symmetry shatters the moment a tree branch strikes a single power line, or lightning grounds a phase. In an unbalanced physical fault, the currents and voltages skew. Solving the resulting differential equations using raw phase variables creates an interlocking mathematical mess that is virtually impossible to compute at scale. In June 1918, a Westinghouse engineer named Charles LeGeyt Fortescue presented a paper at the American Institute of Electrical Engineers Convention in Atlantic City. Fortescue did not offer a rough approximation or a heuristic workaround for these asymmetrical faults. He formulated a strict, complex mathematical translation layer between chaotic physical reality and solvable algebraic equations. His thesis, which came to be known as Symmetrical Components, proved that any unbalanced multi-phase system can be completely decoupled into three perfect, independent sequence networks through the use of matrix algebra. By turning an intractable physical problem into an elegant mathematical one, Fortescue provided the mandatory framework we still use today to calculate short circuits and program microprocessor-based protection relays. To understand how the decoupling works, we start with a complex operator called alpha. Alpha represents a precise 120-degree phase shift. It is the geometric building block used to rotate vectors in the complex plane. This is the Fortescue transformation matrix. Multiplied against three unbalanced phase voltages, we map those chaotic variables into a new mathematical system. It extracts three sets of balanced vectors: positive sequence, rotating standard ABC, negative sequence, rotating reverse, and zero sequence, pulsing perfectly in phase. Because it is a systemic property, a sequence component cannot mathematically exist in one isolated phase. It requires the interaction of all three phases simultaneously. Translating these voltages into sequence coordinates is highly organized, but it is merely the setup. The true power of the Fortescue method lies in how it applies to the grid's physical infrastructure. Changing our basis from physical phase space to mathematical sequence space allows engineers to treat a highly erratic unbalance as a superposition of perfectly symmetrical states. Grid equipment, like overhead lines and generator windings, is defined by its impedance. In a three-phase system, this is represented by an impedance matrix. Look at this 3x3 physical impedance matrix. The values on the diagonal represent the self-impedance of each wire, but the off-diagonal terms represent the mutual inductive coupling between phases. A change in phase A instantly affects phase B, locking equations together. To break this lock, the system requires circular symmetry, meaning the diagonal terms must equal each other, and all mutual off-diagonal impedances must be identical. When we apply the Fortescue transformation and its inverse to this symmetrical impedance matrix, the complex algebraic terms cancel out. The off-diagonal terms vanish, leaving a purely diagonal matrix. The positive, negative, and zero sequence impedances are now completely isolated. The electrical crosstalk is gone. Instead of solving a tangled system of coupled differential equations, engineers can now solve three independent, single-phase equivalent circuits. These mathematically decoupled sequence networks must then map directly onto the physical topology of the actual grid equipment. While positive and negative sequences flow smoothly through the system, the zero sequence network is strictly constrained by physical grounding paths and the internal geometry of transformers. Take the structural design of these large-scale step-down transformers. We classify them by their magnetic cores, distinguishing a shell-type transformer from a three-leg core-type transformer. In a three-leg core-type transformer, the zero-sequence flux generated by the three phases has no low-reluctance iron path to return through. To complete its circuit, it must force its way through the high-reluctance steel tank or the surrounding insulating oil and air. Because magnetic reluctance heavily impedes the flow of flux, this specific physical layout results in a zero-sequence impedance that is significantly lower than the transformer's positive sequence impedance. Due to this low impedance path, a single phase-to-ground fault on the secondary terminals of a core transformer will often generate a higher, more destructive fault current than a complete three-phase short circuit at the exact same location. Today, grid operators face issues beyond steady-state faults. Modern power electronics, like inverters and variable speed drives, introduce non-sinusoidal waveforms and severe harmonic distortion. Fortescue's method applies here too. We can map specific harmonic frequencies to their inherent rotational sequences. The baseline first harmonic rotates in the positive sequence. The cis-harmonic, however, inherently rotates in the negative sequence. Triplen harmonics, multiples of 3, like the third or ninth, are inherently zero sequence. By definition, their wave peaks align perfectly across all 3 conductors at the exact same time. This diagram shows the evolution of those harmonic currents. Even when heavily distorted by a fifth harmonic, the total current remains mathematically balanced, provided the exact same distorted waveform appears at regular 120-degree intervals across phases A, B, and C. To evaluate real-world grids where this balance fails, researchers developed the symmetrical component-based approach. This isolates the specific balance, unbalance, and distortion components for every individual harmonic order. From this, we derive metrics like total phase current distortion. This improves upon traditional total harmonic distortion calculations, providing a single, highly accurate indicator for a heavily unbalanced 3-phase system. By mapping harmonics directly to their sequences, engineers can look at a distorted wave cap and mathematically isolate the exact piece of nonlinear equipment causing the systemic unbalance. We can apply this identical theory down to the endpoints of the grid, heavy industrial electrical machines, like 3-phase induction motors. A healthy induction motor operates efficiently, drawing almost exclusively on positive sequence currents to generate rotational torque, with negligible negative or zero sequence presence. Snap a rotor bar or short a stator bunding, and that perfect magnetic symmetry breaks immediately. The motor begins pulling negative sequence currents, which generate a counter-rotating magnetic field that fights the motor's own rotation. Modern microprocessor-based protection relays calculate instantaneous symmetrical components. They sample the incoming current thousands of times per second, hunting for the exact moment those negative sequence values spike. These same diagnostic principles are being written into the control logic of next-generation 5-phase and N-phase electric drives. By isolating that specific negative sequence signature, a digital relay can detect a microscopic mechanical failure and trip the breaker, long before the heat and vibration lead to a catastrophic mechanical breakdown. At the macro scale of today's modernized grid, the topology is shifting constantly. Wind turbines, solar inverters, and digital relays must maintain stability across an incredibly complex network. Once the independent sequence networks calculate the fault currents, we apply the inverse transformation matrix, seamlessly recombining the isolated solutions back into physical, real-world phase space. Fortescue's method serves as the universal translation layer. It bridges the gap between the chaotic physics of a short circuit and the structured data required by grid operators. The physical analog filters of the 20th century have been entirely replaced by high-speed digital signal processors, but the underlying sequence equations they execute remain identical. More than a century after it was introduced on a boardwalk in Atlantic City, this complex matrix algebra remains the indispensable mathematical lens through which we protect, operate, and stabilize the global electrical grid.